A marine researcher finally has his head above water after resurfacing from a 100-day mission in the Florida Keys.
In April 2025, marine monitoring equipment detected a structural collapse on the ocean floor, just off Florida's Gulf Coast. A large section of the continental shelf gave way without warning, forming a sinkhole over 300 feet wide and estimated to be deeper than 100 feet. This event is one of several similar incidents recorded over the past 18 months, prompting new investigations into the stability of Florida's offshore geology. The affected area had previously been categorized as geologically stable. For decades, the continental shelf was considered passive, with little risk of sudden collapse. Recent data, however, shows that portions of the seafloor are weakening faster than expected. Researchers from NOAA and multiple universities are now monitoring a pattern of sediment shifts, structural faults, and undersea depressions developing along key stretches of the coast. Analysis of sediment cores and sonar imaging has identified several contributing factors. The seafloor in these regions is composed of layered sediments atop ancient limestone bedrock. Much of that bedrock contains voids left behind by Ice Age aquifers, freshwater reservoirs that formed when sea levels were significantly lower. As these voids drain or compact under modern conditions, they become prone to collapse. Another factor is the release of methane gas. Methane is stored within ocean sediments in frozen deposits known as methane hydrates. These hydrates are highly sensitive to temperature and pressure changes. As ocean temperatures rise, even slightly, the hydrates destabilize, releasing methane and weakening the sediment structure above. In affected areas, sonar scans have detected gas plumes and decreased seafloor reflectivity, both indicators of potential instability. The implications extend beyond geological interest. Underwater infrastructure, including power lines, internet cables, and oil pipelines, runs through several of the zones now under review. Some collapse sites have occurred within 50 to 100 meters of these installations. As a precaution, agencies have begun expanding undersea monitoring networks and reevaluating risk models for critical systems. This new understanding of Florida's offshore terrain is leading to a reassessment of both natural hazard risks and long-term coastal planning. While it's unclear how widespread the problem may become, researchers agree that what was once considered a stable foundation is now showing signs of structural decline. Ongoing studies aim to map additional weak zones and determine the potential for future collapses along other parts of the Gulf and Atlantic seaboards. Over the past year, marine researchers have confirmed the appearance of multiple large sinkholes forming along Florida's offshore continental shelf. These aren't small, gradual depressions. They're wide, deep, and in some cases developing within days. The largest recorded collapse in 2025 spanned over 300 feet across and dropped more than 100 feet deep. These events are part of a growing trend that is changing how scientists understand the stability of the seafloor in this region. Many of these underwater sinkholes are forming in areas previously considered geologically stable. The continental shelf along Florida's west and southeast coasts had long been viewed as a passive margin with little seismic or structural activity. That view is now being reevaluated. With the help of sonar scans, remote-operated submersibles, and sediment analysis, researchers have mapped a pattern of structural weakening across multiple zones, particularly in areas with older sediment layers and underlying limestone bedrock. One major factor behind these sinkholes is the collapse of underground cavities left by ancient freshwater aquifers. These aquifers formed during past glacial periods when sea levels were lower and groundwater filled subterranean limestone voids. Over time, as sea levels rose and climate conditions changed, these spaces began to dry out and destabilize. Now, with modern sediment pressing down and additional forces at play, the ceilings of these caverns are beginning to collapse. In addition, researchers are observing methane gas releases in the same regions where these collapses are occurring. Methane hydrates, solid structures of water and methane found in ocean sediments, are sensitive to changes in temperature and pressure. When these conditions shift, the hydrates break down, releasing gas that can undermine the integrity of surrounding sediments. The result is a weakening of the seafloor's structural support, which increases the likelihood of sudden collapses. While these events are still relatively rare, the speed and unpredictability with which they occur is causing concern. Some of the sinkholes have formed close to undersea infrastructure, including data cables, communication lines, and sections of pipeline. In response, Florida officials and federal agencies are expanding underwater monitoring, adding new sensor arrays, and increasing drone surveys of coastal zones considered high risk. These developments suggest that Florida's underwater terrain is not as stable as once believed. Continued research is underway to assess whether these sinkholes are part of a larger regional shift or the result of local, isolated geological changes. Either way, understanding the full scope of the threat will be essential for protecting coastal communities, infrastructure, and marine ecosystems that depend on the health of the continental shelf. Recent studies along Florida's continental shelf have identified the release of methane gas from the seafloor as a contributing factor to sediment destabilization and underwater sinkhole formation. These methane emissions are occurring in areas where the seabed contains large deposits of methane hydrates, solid compounds formed from methane and water that exist under conditions of high pressure and low temperature. Methane hydrates are naturally occurring and relatively stable under consistent conditions. However, when ocean temperatures increase or pressure levels shift due to sediment movement or collapse, these hydrates can break down and release methane gas into the surrounding sediment and water. This release can weaken the structural integrity of the seabed by reducing friction, creating voids, and increasing pore pressure within the sediment layers. Sonar imaging and remote-operated vehicle ROV surveys have confirmed the presence of active methane seeps across several sites along the Florida shelf. These seeps appear as vertical plumes of bubbles rising from the sediment into the water column. In some areas, the release of gas has coincided with newly formed seafloor depressions or cracks, suggesting a direct relationship between methane hydrate breakdown and seafloor instability. Geological data collected over the past year also shows a correlation between methane emission zones and locations of prior or ongoing sediment collapse. Some researchers believe that these emissions may not only weaken the sea floor over time, but could also trigger rapid failures in areas where hydrate concentrations are high. The concern is that methane releases, especially if occurring over a wide area, might contribute to a cascading collapse effect along the shelf edge. The environmental impacts of methane release are also being studied. Methane is a potent greenhouse gas, significantly more effective than carbon dioxide at trapping heat in the atmosphere over short periods. While most of the released gas in deep water tends to dissolve before reaching the surface, the scale and rate of release may still have localized ecological impacts, particularly in regions with low oxygen or sensitive marine habitats. Researchers are now prioritizing hydrate-rich zones for expanded monitoring. Using heat flux sensors, sediment cores, and time-lapse sonar scans, teams are working to build predictive models that identify early signs of hydrate destabilization. These efforts are aimed at improving understanding of the conditions that lead to methane-driven erosion and preventing unexpected infrastructure risks offshore. As climate trends continue and oceanic conditions evolve, methane hydrate behavior is likely to play a larger role in coastal geological assessments, not just in Florida, but across other continental margins worldwide. Another factor contributing to the collapse of the seafloor along Florida's continental shelf is the failure of ancient subterranean aquifers. These aquifers, formed during past glacial cycles when sea levels were much lower, once held large volumes of fresh water within porous limestone formations beneath the seabed. As ocean levels rose and groundwater flow patterns shifted, many of these aquifers became isolated and began to drain or slowly compact. Today, what remains in some areas are large underground cavities that are no longer structurally supported. As sediments continue to accumulate above these voids, the pressure increases and the limestone ceilings eventually fail. When this happens offshore, it results in a sinkhole or collapse zone, sometimes spanning hundreds of feet and occurring with little to no warning. Recent sonar mapping and core sampling have identified several of these features off both the Gulf and Atlantic coasts of Florida. Many are associated with known karst formations, geological structures composed of soluble rock such as limestone, which naturally form underground voids over time. Similar features are common across inland Florida, where sinkholes are well documented. What is less understood, however, is the scale of these cavities offshore and the rate at which they are becoming unstable. In addition to passive erosion, researchers believe that the gradual movement of salt water into these once freshwater systems is playing a role in weakening the surrounding rock. Saline intrusion can alter the chemical stability of limestone, accelerating dissolution and increasing the risk of collapse. Over time, the brackish transition zones created by this intrusion may form weak points across large areas of the continental shelf. Unlike surface sinkholes, which can often be spotted early by ground deformation or surface cracking, undersea aquifer collapses are harder to predict. They typically occur out of sight and may not be detected until after the collapse has happened. This makes real-time monitoring critical in areas near underwater infrastructure or heavily trafficked marine zones. To better assess these risks, researchers are expanding the use of sub-bottom profilers, seismic reflection tools, and 3D geological modeling. These technologies allow scientists to map voids and track changes in sediment structure over time. The goal is to better understand which regions may be at greatest risk and how ancient aquifer collapse might impact broader coastal stability. As monitoring continues, these findings are contributing to a revised understanding of Florida's subsurface geology. What was once considered a dormant layer of buried history is now being recognized as a potential trigger for sudden and widespread seafloor instability. As seafloor collapses and sediment instability increase along Florida's offshore shelf, marine ecosystems are facing new and growing pressures. One of the most immediate biological consequences is the expansion of so-called dead zones, areas of ocean where oxygen levels drop so low that most marine life cannot survive. These hypoxic zones are not new to the Gulf of Mexico or the Atlantic coast, but recent changes in seafloor structure appear to be accelerating their development in Florida's coastal waters. When a portion of the seafloor collapses, it often triggers a cascade of environmental disruptions. Sediment clouds rise into the water column, smothering coral reefs, seagrass beds, and filter-feeding species like sponges and shellfish. As this material settles, it can create a physical barrier over habitats and reduce water flow, limiting oxygen exchange. In addition, methane and other gases released during sediment disruption can alter local chemistry, further reducing available oxygen. Some of the released gas dissolves in the surrounding water, affecting pH levels and contributing to acidification. Combined with the organic matter stirred up from the seabed, this can create the perfect conditions for oxygen to be consumed faster than it can be replenished. Field observations from recent NOAA missions have confirmed that some collapse zones are now surrounded by low oxygen areas that were not present in earlier surveys. In these regions, researchers have reported declines in fish populations, invertebrate die-offs, and visible signs of reef degradation. In some cases, entire patches of once active reef have turned into bare, uninhabited rock. Seagrass beds, which act as nursery grounds for countless marine species, are also at risk. When buried under sediment or exposed to declining oxygen, these beds can die off quickly. Their loss not only impacts biodiversity, but also affects water clarity, coastal erosion resistance, and carbon storage capacity. Scientists are currently expanding monitoring in these impacted areas, using oxygen sensors, remotely operated vehicles, and time-lapse photography to document changes. While the long-term consequences are still being studied, early results suggest that biological recovery in these areas is slow and in some cases may be limited unless conditions improve. The expansion of hypoxic zones along Florida's coast highlights the interconnected nature of geological and ecological systems. What begins as a physical collapse beneath the ocean floor can ripple outward, affecting entire ecosystems above. Understanding these patterns is now a top priority for marine researchers and environmental managers working to protect the long-term health of Florida's coastal waters. The geological changes taking place beneath Florida's offshore waters are beginning to raise concerns not only for marine life, but for the infrastructure and communities that depend on stable coastal conditions. As sinkholes and collapses continue to affect parts of the continental shelf, researchers and state officials are turning their attention to how these undersea changes may impact land-based assets, including residential areas, ports, and critical utilities. Recent surveys using multi-beam sonar and satellite-based altimetry have detected small but measurable shifts in the seafloor just offshore from densely developed regions. These shifts include widening fractures, pressure-related sediment slumping, and fault-like movements in zones that were previously considered structurally inactive. In some areas, these cracks and deformations have been observed within several kilometers of high-value coastal real estate and industrial facilities. While most of these geological features remain underwater, the proximity to the coastline has prompted additional studies to determine whether similar conditions could exist beneath urban or suburban areas built on porous limestone. Florida is already known for its susceptibility to inland sinkholes due to karst topography. But the link between offshore subsidence and onshore stability is now being re-examined with new urgency. Infrastructure systems face specific vulnerabilities. Submarine power lines, fiber optic data cables, and fuel pipelines run through or near some of the underwater zones where structural changes have been confirmed. If a significant collapse or crack occurs near one of these corridors, the impact could be immediate, ranging from data outages to utility disruptions. In 2025, one monitoring station in the Eastern Gulf recorded a sediment slump less than 30 meters from a main fiber optic path. While no damage occurred, contingency plans are now being updated across the region. Port facilities, which rely on stable seafloor conditions for shipping lanes and moorings, are also watching the situation closely. Unexpected shifts in channel depth or seabed composition could create hazards for navigation or require costly maintenance. Meanwhile, insurance underwriters and developers have begun reassessing coastal risk models in light of the evolving data. Urban planners are now incorporating geotechnical monitoring into their assessments of future coastal projects. Some cities are exploring expanded use of ground-penetrating radar and sub-bottom imaging to identify vulnerabilities in coastal foundation zones. These efforts are part of a broader move to link marine geological data with land-based development strategies. While there is currently no evidence of direct structural risk to inland buildings from offshore collapses, experts emphasize that the seafloor changes highlight the need for better integration of coastal science into infrastructure planning. Understanding what's happening beneath the surface is increasingly important for maintaining resilience above it. Alongside the structural concerns tied to shifting sediments and seafloor collapses, marine biologists are also tracking significant changes in Florida's coral reef systems. In recent years, certain reef zones, especially those near underwater sinkhole sites, have shown accelerated signs of stress, fragmentation, and in some cases, abandonment by native marine species. These areas are being informally referred to by researchers as ghost reefs. Ghost reefs are sections of coral habitat that still have the structure of a reef, but lack the vibrant biodiversity typically associated with healthy reef systems. These reefs often appear lifeless or sparsely populated, with bleached coral skeletons, thin biofilm layers, and reduced fish populations. Many were once thriving parts of Florida's barrier reef system, but recent observations show that sediment fallout and localized changes in water chemistry have played a role in their decline. When portions of the continental shelf collapse or erode, they release plumes of fine sediment that can travel significant distances underwater. These particles cloud the water, reduce light penetration, and settle onto coral surfaces. If the sediment remains too long, it can block photosynthesis in symbiotic algae, zooxanthellae, and cause coral to expel them, a stress response known as bleaching. If recovery conditions are not favorable, the coral does not survive. In addition to sediment, sudden shifts in the seabed can displace or tilt reef platforms. This physically stresses coral colonies and alters water flow, making it harder for larvae to settle and grow. In some cases, formerly elevated reef structures have partially collapsed into deeper water, beyond their normal range for survival. Monitoring stations off the Florida Keys and southeast coast have documented at least a dozen such ghost reef formations since 2022. These findings are especially concerning because reefs serve as natural wave buffers, biodiversity hubs, and economic engines through tourism and fisheries. Their decline could compound the vulnerabilities already posed by geological instability. Researchers are now studying the connection between reef health and the growing network of seafloor disturbances. Remote imaging, water sampling, and diver surveys are being used to determine whether some reefs are located near methane seeps or brine flows that may be altering water chemistry beyond what traditional ocean warming can explain. Efforts are also underway to identify coral species that may be more resilient to sediment and chemical stress. Restoration programs are testing hardier coral strains and exploring artificial reef designs that can be placed away from high-risk areas. However, experts warn that without understanding the root causes of reef system disruption, restoration alone won't be enough. The ghost reefs of Florida are a visible marker of deeper changes underway offshore. As sediment movement, gas release, and hydrological shifts reshape the ocean floor, the ecosystems built on those foundations face uncertain futures. While mapping seafloor changes off Florida's coast, scientists have identified the formation and expansion of underwater brine pools, highly concentrated pockets of salt water that accumulate in natural depressions on the ocean floor. These pools, sometimes referred to as death zones, form when hypersaline fluids seep upward from deep within Earth's crust, often through faults or cracks opened by sediment collapse. Brine pools are naturally occurring, but their appearance in areas experiencing geological disturbance is drawing new attention. Unlike the surrounding seawater, these pools are so dense that they don't mix easily with water above. This creates isolated zones with significantly different chemical compositions, including high salinity, low oxygen, and sometimes toxic levels of hydrogen sulfide or methane. Marine life that accidentally enters these zones typically cannot survive. Research vessels operating in the Gulf and Atlantic coastal waters of Florida have documented multiple instances of fish, crustaceans, and bottom-dwelling organisms found dead near the edge of these pools. In some cases, entire seafloor sections around the pools are covered in the remains of marine animals, signaling rapid biological die-off. What makes these features especially concerning is their potential connection to larger seafloor changes. Many brine pools appear to be forming in or near areas already affected by sinkholes, gas releases, or aquifer collapse. This suggests a systemic breakdown of geological stability beneath the seafloor, where deep fluids are migrating upward through weakened rock layers. Some brine pools have grown large enough to be seen on high-resolution sonar scans as flat, shimmering basins. The edges of these formations can also erode into surrounding sediment, gradually expanding their footprint. In other cases, seepage from below has caused new pools to emerge in previously unaffected zones. Researchers are studying the chemical composition of these pools to better understand their origins. Core samples taken from nearby sediments reveal mineral traces and isotopic signatures consistent with deep buried salt domes, ancient geological structures made of evaporate layers from prehistoric seas. As pressure and temperature shift underground, fluids trapped in or around these domes begin to move, carving paths toward the seafloor. These dynamics carry potential consequences not just for marine life, but also for seafloor integrity. Brine can weaken surrounding rock, increase erosion, and trigger small-scale collapses. If multiple brine zones continue to grow or intersect with active fault systems, they could contribute to broader instabilities across the seafloor platform. For now, teams are deploying more instruments to monitor brine activity in real time. Early warning systems based on salinity sensors, underwater chemical detectors, and satellite-supported surveillance are being tested in high-risk areas. Florida's brine pools are a reminder that what happens beneath the surface isn't always visible, but it can be just as disruptive as events above. These toxic pockets represent a unique challenge in the effort to understand and manage the evolving risks along the state's coastal shelf. While Florida is not typically known for seismic activity, recent offshore monitoring has revealed a pattern of small, low-frequency tremors occurring near regions of seafloor instability. These microquakes, some too weak to be felt at the surface, are being recorded by an expanding network of ocean bottom seismometers and geophysical sensors installed to study the ongoing geological changes beneath the continental shelf. In early 2025, researchers from multiple institutions, including USGS and several Gulf Coast universities, began publishing data on these subtle seismic shifts. Although they measure less than magnitude 2.0, their consistency and location are causing experts to take a closer look. Many of the tremors are occurring along previously unmapped or poorly understood fault systems running parallel to Florida's coast, especially in zones where sediment collapse, methane release, or brine movement has already been observed. What makes these events notable is not their size, but their frequency and potential to indicate broader tectonic changes. Small seismic movements can signal adjustments in subsurface pressure, fault creep, or stress redistribution, all of which may precede larger geophysical activity. In Florida's case, the concern is that weakening of the seabed from gas releases or structural shifts could trigger a domino effect along these fault zones. In at least 2 instances, sonar data has revealed minor vertical displacement on the seafloor, essentially tiny shifts in elevation that align with the timing and location of recorded microquakes. While these movements are measured in centimeters, they suggest that underground forces are slowly reshaping the region in ways not previously anticipated for Florida's geologic profile. Some of these offshore faults may be relics of older plate boundaries or rift systems, long considered dormant. However, new studies suggest that rising ocean temperatures, shifting sediment loads, and subsurface chemical activity may be reactivating these ancient features. If even partially correct, this could lead to increased fault activity over time, especially in zones already weakened by human activity, such as offshore drilling or high-volume shipping lanes. Emergency planners are taking notice. Although the risk of a large earthquake remains low, the potential for secondary impacts, such as undersea landslides, disruption of infrastructure, or localized tsunami-like effects, is enough to warrant additional research and contingency planning. To respond, a regional seismic mapping effort is underway, combining satellite data, seafloor pressure sensors, and deep earth modeling. The goal is to better understand the fault geometry, stress fields, and seismic behavior of Florida's offshore regions. The presence of microquakes off Florida's coast challenges the long-standing assumption that the area is tectonically inactive. It suggests that the state's underwater environment may be more dynamic and more responsive to environmental changes than previously thought. As Florida's underwater landscape continues to shift, it's not only geological hazards that are being uncovered. In the wake of sediment collapses and seafloor erosion, researchers are finding fossilized remains and traces of ancient marine life that had been buried for tens of thousands or even millions of years. These unexpected discoveries are offering scientists a rare opportunity to study prehistoric ecosystems that once thrived in what are now deep marine zones. In several recently exposed underwater sinkholes and slope failures along the Gulf and Atlantic shelves, divers and submersible teams have retrieved fossilized coral, mollusk shells, megalodon teeth, and even segments of ancient seagrass beds preserved under layers of compacted sediment. In one notable find from early 2025, marine archaeologists exploring a collapsed shelf edge near the dry Tortugas, recovered vertebrae belonging to what appears to be an extinct species of whale-like marine reptile, possibly dating back to the Miocene epoch. While such fossils are typically found on land due to ancient sea level changes, these new finds remain in their original context, embedded in marine sediments, undisturbed for ages until now. These fossils are more than just paleontological curiosities. They are helping scientists reconstruct the history of Florida's coastal evolution, including past sea level rise, ocean chemistry changes, and species migration patterns. Some microfossils, such as foraminifera and plankton remnants, are being used to model prehistoric climate data and track long-term trends in ocean temperature and acidity. Researchers are also investigating the possibility that parts of Florida's submerged shelf once supported shallow lagoons and mangrove systems similar to modern Everglades environments. If confirmed, this would mean that some regions now 50 or 100 meters underwater were dryland or coastal marshes during the last glacial maximum. In addition to ancient animal remains, sediment cores taken from freshly exposed areas have revealed preserved pollen, plant fibers, and even trace organic compounds, providing a record of vegetation and terrestrial life that once existed along now submerged coastlines. These findings are helping bridge gaps in Florida's archaeological and ecological timelines, particularly periods for which little land-based evidence remains due to development or erosion. These discoveries also raise important conservation questions. With more of the seafloor opening due to geological movement, researchers are racing to document and protect vulnerable fossil beds before they are scattered by currents or buried again by sediment shifts. What began as an effort to understand geological risk has now become a window into a long-lost version of Florida, one where ancient marine reptiles swam in shallow coastal waters, and coral gardens thrived in conditions far different from today's rapidly warming seas.